Okay, some of you missed the explanation, absent, or maybe you need to review it anyway. The end of uh, chapter 5, section 2, there is a section on derivatives of integrals and integrals of derivatives. And I went through this pretty carefully in class. I just want to make sure if you weren't there, you can do it and understand. The point of this is to get to the shortcut to this. So I've made a function here that we can take the derivative of, or we can do the antiderivative of, and we can see what happens on this. Okay, so the function is of t, and the first thing it says to do is find the antiderivative in this example. So we're doing this function, we're going to do the derivative of the antiderivative and the antiderivative of the derivative. And it makes a difference which order they're in. Seems like they should just cancel and be gone, but we need to keep track of what's really going to happen here. So the antiderivative of this is 1 half of 1 over t, and antiderivative of that is ln. So I'm not doing the derivative yet. So it's going to be 1 half ln of t. And this is t to the 1 half, so its antiderivative would be raise the power by 1. So it's t to the 3 halves divided by 3 halves, or times 2 thirds. And we're supposed to evaluate this between 4 and x. So we haven't done the derivative yet. And so we put x in for the t's, and we get 1 half ln, this should have been of the absolute value of x, because we're putting x in for the t, plus 2x to the 3 halves over 3. So that's putting x into all this. Minus, now we got to put 4 into this, so that's 1 half ln of absolute value of 4, which is 4. Anyway, plus 2 times 4 to the 3 halves over 3. Okay. Now we're going to take the derivative of this. So the derivative of ln of x is just 1 over x, so we get 1 over 2x. And the derivative of this, we take the 3 halves down, so that would cancel the 2 thirds and lower the power of 1, and so that becomes x to the 1 half, or square root of x. And then the derivative of that, that's a constant. Derivative of that, that's a constant. And so we get 0 and 0, and so we're subtracting 0, so we get this, which looks like the original thing with x put in place. Cut it out. With x replacing the t. And that's a key thing to realize. If I have the derivative of the function from 4 to x, the 4 part gone, and the x just replaces the t in the original function, and then the derivative does cancel this, and we end up with the same function, only with x in it. Now, let's do it the other way. We don't get quite the same result. Take the derivative first. So if this is 1 half t to the minus 1, its derivative is take the minus 1 down times and lower this by 1. So the derivative would be We're not doing the integral yet, so I'm writing that. It'd be minus 1/2 t to the minus 2, and then the derivative of t to the half is 1/2 t to 1 less, t to the minus 1/2 dt. And now I've got to integrate it. So if I integrate this, this is going to go right back to 1 over 2t, or to this. So it's going to be 1 over 2t. And if I integrate that, it goes right back to square root of t, or t to the 1/2. And now I've got to put in my limits, 4 to x. So if I put x in there, I get 1 over 2x plus square root of x minus, I put 4 in, I get 1 over 2 times 4 plus the square root of 4. Well, this part is the same as the original function, but I get the constant this time. When you integrate, you get the function plus a constant if you're putting in a constant. The constant disappeared when I took the derivative after I integrated it. No constant up here. But here, when we do the integral after doing the derivative, we get a constant. So again, we get exactly the same function back, but here we get it with minus with the 4 put in. Here we get exactly the same function back, but no, the 4 had no bearing on it because we took the derivative afterwards. Okay, let's do it again. This time there's x in both limits. So then this is not going to be a constant. We'll get something out of this, and we'll get a variable in here, and this part here that was a constant won't be a constant. It'll be a variable, and so we'll get 2 parts here. There's something else that shows up with this also, and so we'll work through this one. First, integrate. So the antiderivative of that, raise that to 3 and divide by 3, so it's 5/3 t to the 3 plus t squared, because the derivative of t squared is 2t. We've got to evaluate that from x squared to 3x to the 4th. So we plus 3x to the 4th in for the t's. And I'm not going to simplify this because I want you to see what's going to happen here. So I'm going to write in 3x to the 4th. Oh, I forgot to put in, haven't done the derivative yet. 3x to the 4th to the 3rd plus putting 3x to the 4th in for the t squared. So I've got this, and I got to subtract. Now I got to put in x squared in for these. So I got 5/3 x squared to the 3rd. And I could simplify that, but I'm not going to. Plus x squared squared, putting x squared in for the t. And I've got this whole worked out. Now I got to take the derivative. Now when I take the derivative of this, the 3 is going to come down, cancel the 3, and I'm going to get 5 this to the 2nd. 5 times 3x to the 4th to the 2nd times the derivative of the inside. which is 12x to the third, because of the chain rule. And when I take the derivative of this, it's going to be 2 down times this to the 1. So it's going to be plus 3, 2 down, so it's 2 times 3x to the fourth to the 1. Take the power down to this to 1 less times the derivative inside. So, this is times this 12x to the third also. So I'm going to move this parenthesis and say this is times both of these, because both of these had the derivative of the inside. Chain rule makes that 12x to the third. And then I got minus. Now I got to take the derivative of this. Well, the 3 is going to come down, cancel the 3. So I'm going to get 5x to the second to the 2 times the derivative of the inside, so it's times 2x, plus derivative of this, and it's minus all of this, so I better put parentheses, minus all of this. Derivative of this is going to be 2 times x squared times the derivative of the inside, 2x. So I'm going to have 2 times x squared. Now, I know I could have called this x to the fourth and did 4x, but I want to leave this out because the chain rule is saying I have to do the derivative of the inside. So I want you to see what we got, and you couldn't see because I'm off the paper. My original function was 5t squared plus 2t, and I was going from x squared to 3x to the fourth. Notice I've got exactly that, 5, that in for the t, squared, that in for the t. I got exactly the same thing, except that I had the derivative of the inside times that. Minus, and then I had to put x squared in, and that's what I ended up doing, putting x squared in for those, but I had the derivative of the inside, the x squared here. So what I get is the original function with this put in for the t's, and then minus this put in for the t's. But when on this part, I have to do times the derivative of this. And for this part, when I put that in and subtract it, I get x squareds in it, like I did, but also times the derivative of that because of the chain rule. So all I do is put this in for the t's and then put this in for the t's and subtract that from the other one, but multiply by the derivative of this. That's when the derivative comes after I integrate. What happens if I put the derivative first? Well, that means I need to take the derivative of this, which would be 10t plus 2. And then I got to integrate that from x squared to 3x to the fourth. Well, if I integrate that, it goes right back to 5t squared plus 2t evaluated from x squared to 3x to the fourth. And so I get this put in for the t, 5 times 3x to the fourth squared plus 2 times 3x to the fourth minus x squared put in there, so I got 5 times x squared squared plus 2 times x squared, and I get just this put into the t's, and then minus this put in for the t's. And that one is pretty straightforward. There's no chain rule process because I'm not taking the derivative after I put these in. I'm taking the derivative first and then putting these in and then integrating. Or integrating and then putting those in. So I don't have the chain rule problem. So here's something I can't do I might be able to, but don't want to have to integrate or differentiate. And I've noticed that I just get the same functions back. I just have to note what to do when the derivative is on the outside or on the inside. When it's on the outside, and if the a is just a constant, it's not going to be a problem because when I take the derivative of a into a function, it's going to be gone. So this is going to be simply, I would integrate this into some crazy mess, and then I'd have to take the derivative, would go right back to this, and I'd be plugging this in. And when I plug a in and take the derivative, it's going to be gone. So I'm just going to have ln of, replace the t with 2x to the third plus 2 arc sine, and putting 2x to the third in for the t's, tangent of 2x to the third over 2x to the third. But I took the derivative afterwards, so I have to take times the derivative of what I put in, which was 2x to the third. The derivative of that is 6x squared. So all of this would have been times 6x squared. And that would be my answer. Now, if this had a variable in it, I'd have to put that x squared, whatever it is, in for the t's also, and times it by the chain rule, the derivative of it. But the derivative of a constant is 0, so that's all gone. So I don't need it. So that's the answer to that one. And the answer to this one, if I take the derivative first and then integrate it, I put this in, and I get ln of 2x to the third plus 2 arc sine of tangent of 2x to the third over 2x to the third. Oh, over that, there. So I put that in, put the a in, and since I'm doing it after I do the derivative, the a will show up, and so I have to put all of this ln of a plus 2, replace the t with an a, absolute value, arc sine of tangent of a over a. And that's how that one will work. It's a little bit tricky stuff there. It's not real clear in the text how that works, so I kind of wanted to show you this. Okay.